Okay, let me begin just with a quick recap. Yesterday we started off with the new topic of dielectric materials. And these are materials that serve a couple of different purposes. One, to store charge. And secondly, as insulators in various applications. So charge storage devices, capacitors, things like that, we make use of dielectrics. And then we had looked at what are dielectric constants or relative permittivity, what is the different mechanisms. We had started considering one, the electronic polarization, and we had tried to relate the macroscopically observed phenomena of the relative permittivity or the dielectric constant epsilon r to the microscopic electronic polarizability through an equation that was called the Clausius-Mossotti. Did I get to Clausius? No, we didn't get there. Okay, we're going to come to it. But we ended up with an equation that gave us, actually it's very close to the Clausius-Mossotti. We are one step away, basically. This is what we had last when we ended, namely a relationship between the relative permittivity and the polarizability. What we'll look at today is a modification of this, taking into account something that we had made certain assumptions in arriving at this, and we're going to modify this equation to arrive at what is known as the Clausius-Mossotti equation. The electronic polarizability. Right? We saw that when the electron cloud, which is lighter, normally if you think of it as the atom, the positive charge is center and the negative charge, they coincide, but under the application of an electric field, they will separate out because the electrons being much lighter, and so you get a dipole moment that is created. And that mechanism has a term, the polarizability, electronic polarizability, which is alpha E. N is the number of molecules per unit volume. That's yesterday. Did you miss yesterday? Okay, no wonder. So there will be lots of questions. You better go back and check with somebody what was done yesterday. Otherwise, I'll be repeating the whole lecture. Okay? So we'll begin from there. The basic assumption that we made yesterday was that the electric field that is applied externally is sort of uniform throughout this material. And that's an approximation. But when we look at, for each individual dipole, what is happening, I mean, over an average of 1,000 molecules or whatever it is there, that value comes out to be okay to use. But for a particular dipole that is situated inside, surrounded by other dipoles, the field that it experiences is not, strictly speaking, the applied electric field. So what we will see is that if you look at it, a periodic arrangement of dipoles, we go up and down around this average value, which is the applied field. So if you average it out, it comes out to be the applied field. But for various reasons, namely the individual dipole that is there is going to experience the dipoles around it, and so the local field is going to be rather different from the field that we are looking at, namely the applied field, which we had, the overall field. Okay, so once we have induced this dipole, we are going to have a change. And we are interested in knowing what is the local field that a particular dipole experiences. And this will depend obviously on the applied field. And it will depend on the crystal structure. It will depend on the applied field in that whatever you've applied is what is going to be the average value, and that's what's going to induce the dipoles. And the larger is E, the larger is the average dipole moment. It will depend on the crystal structure in that all these dipoles that are around it are arranged as part of some crystalline structure, if we are considering a crystal, or if it's a gas, then we don't have to worry about it. So in that process, the exact influence of these other dipoles that are around this particular dipole that we are concerned about will depend on the crystal structure. And to that extent, we have to worry about what is the crystal structure. Now, if you're considering a cubic structure or something that has no structure, for example, a liquid, things can move around very freely. In either of these cases, without going into the extreme details of it, we can write that the local field is equal to the applied field plus 1/3 epsilon naught times the polarization. The local field is equal to the applied field plus 1/3 epsilon naught times the polarization. This local field is also known as the Lorentz field, and in the case of the electronic polarization and ionic polarization, all it is applicable, though when we start talking of orientational polarization or dipolar polarization, this will not be applicable, this idea, to relate it in this way. But at least for some of the polarization mechanisms, namely one which we have looked at, electronic, this idea will apply for a cubic structure, and or if there is no structure, namely in the kind of a liquid situation. Using this idea, then, we can write that P induced, which is the induced dipole moment, here it's a small p, okay, instead of it being dependent on the applied field as before, we are making the correction here that it is dependent on the local field. Previously we assumed for any individual dipole, the dipole moment was given by alpha E times the field from the previous lecture. Now last time what we did was, to arrive at the particular expression out here, we had done a number of steps and arrived at this expression, but it involved the idea that the induced dipole moment, small p, is equal to alpha E times the applied field. What we are doing is we are making a correction here for the applied field and actually using the real field that that particular dipole will experience, namely the local field, which we just expressed in terms of the applied field and the polarization. And we earlier defined susceptibility, electric susceptibility, was defined in terms of the following, that the polarization is equal to, here we have the capital P, polarization is equal to chi, which is susceptibility, epsilon naught times the applied field. So the definition of susceptibility comes out of this equation, and it is not affected by our consideration of a local field. We can still use the external, the average value that is applied. So I've got this equation unaffected by the fact that each individual dipole is now affected by a local field and not simply by the average field. So now what I can do is, I have epsilon r is equal to 1 plus chi e from before. Chi e is unchanged because I haven't changed anything in this definition of chi e. This is still the applied field and not the local field. So this remains the same because this remains the same. We also know that polarization is equal to n times P induced. N being the number of molecules per unit volume, and we've got, these are the induced dipoles, dipole moments. So when we multiply it there, we get polarization. This is also known to us. All these are known. All we have done is made a change in the value of the dipole moment there. So now in this equation here, I'm going to change and substitute for P induced, where earlier I had it as alpha E times the applied field. This time it's going to change and become P induced is equal to alpha E times the local field. So when we make that substitution, we will end up that polarization is equal to N, the number of molecules per unit volume, times alpha E, all right, which we had here, times the local field. And now again I can substitute for the local field in terms of what we obtained in expression, namely the applied field plus 1/3 epsilon naught times the polarization. Okay? So this is the new expression that you're obtaining. Instead of it being simply n alpha E, we've got a second term that is now coming in there, n alpha E times polarization by 3 epsilon naught to account for the local field in this case. So it's a small change from before, but it will affect the results. Also, we know from before that P is equal to epsilon r minus 1 times epsilon naught E. It's simply a variation of this equation where we have substituted for chi E in terms of epsilon r minus 1. It's the same equation that I've rewritten in terms of epsilon r rather than in terms of chi. So I have these two equations, one which says P is equal to n times the polarizability, that's in terms of the alpha, and I've got another one that relates it in terms of the relative permittivity or the dielectric constant. And if I call this equation 1 and this one 2, what we can see is I am going to rearrange this equation 1 and write it as P minus this P term. I'm going to bring them together. I'm just illustrating the steps. It's not very difficult. So we've got this expression is equal to n alpha E. And what we'll do is solve it for P. Times the field. Simply rearranging the equation. Okay? So from that we can write then that P dividing the right side of this equation that we just obtained, namely n alpha E times the field, and dividing it by 1 minus n alpha E 3 epsilon naught, that polarization is equal to n alpha E times the field by 1 minus n alpha E by 3 epsilon naught. So this is another equation that I've got that gives me P. I've just rearranged it. It's basically this equation, but it gives me P on one side. All right, I took that first equation there and modified it to obtain this. And we already have the second expression here, namely P is equal to epsilon r minus 1 times epsilon naught field, which was my earlier expression number 2. So when we equate these two, both are polarization, what we will arrive at is n alpha E times the field by 1 minus n alpha E 3 epsilon naught is equal to epsilon r minus 1 epsilon naught times the field. Okay? And then if we work with this some more, we end up with the following expression, where I'm now going to separate out epsilon r, which we have there, and we will get epsilon r minus 1 by epsilon r plus 2 is equal to n alpha E by 3 epsilon naught. This is the final expression that by equating these two steps, polarization in terms of the electronic polarizability, polarization in terms of the relative permittivity. And when we equate that and rearrange it, this is the expression that is obtained. This is known as the Clausius-Mossotti equation. Excuse me. Now we can compare that with the expression that we obtained yesterday by simply considering the average field or the applied field. Okay? This is what we had. Epsilon r is equal to 1, or epsilon r minus 1 is equal to n alpha E by epsilon naught. But today, by considering the fact that each dipole experiences a local field which is different from the average field, we arrive at a different expression, but nevertheless one that gives us a relationship as before between this observable, measurable, macroscopic quantity and the microscopic quantity that gives us some idea of the particular mechanism that is involved. Namely, it's an electronic polarization, so we use n alpha E. So basically the difference between these two is that the first expression, where we did not account for a local field, underestimates the value of epsilon r that we can obtain. We will see that in a second, that what if you had the same information and you used this equation to calculate epsilon r without considering the local field, or if you actually use this expression, Clausius-Mossotti equation, to calculate epsilon r, what would you get? And we'll see that Clausius-Mossotti gives you a higher value of the dielectric constant than the earlier approximation. Let's consider a simple example by way of illustrating this. If you have argon, we know that that's a gas under normal conditions. But if you cool it to less than 84 Kelvin in temperature, we begin to form a solid. Okay? Now, if you take this argon and look at its properties, it's got a density 1.8 grams per centimeter cubed. And the atomic mass of argon is known, namely 39.95. And given that alpha E, the electronic polarizability of argon, is 1.7 into 10 to the power minus 40 farad meter square. Those are the units there, incidentally, of the alpha E. What we want to do is to calculate epsilon r for solid argon. And we would like to see this by using the earlier approximation, what we did yesterday. Simply epsilon r is equal to 1 plus the n alpha E by epsilon naught. And the new equation, Clausius-Mossotti equation. So if we simply look at it, the main information that I need in either case, I've got alpha E, I've got epsilon naught, which is known to me. I'm trying to calculate this. The only thing that I really need to know is n. How many atoms are there in the molecule in that given volume? Or how many molecules are there? In this case, we're considering an atom. So how many atoms are there per unit volume? So we need to determine n. That's the main goal. Everything else is given. And you can do that given the information about the atomic mass and density. You should be able to calculate the number of atoms and given Avogadro's number. So 1 mole, namely 39.95 grams, contains so many atoms. And when you know how many atoms are there in so many grams, you can convert that using density into a volume. So you get the number of atoms in per volume, and you can calculate that. So by doing that, namely that you will get n is equal to Avogadro's number divided by mass times the density, you will get it's equal to 2.71 into 10 to the power 22 per centimeter cube. Okay, so you got n. And you've already got alpha E, you know epsilon naught. And if you use these numbers to calculate, from the first equation where we had simply epsilon r is equal to 1 plus n alpha E by epsilon naught, the calculation will yield us a value of 1.52 for the relative permittivity for argon. Okay. On the other hand, using the Clausius-Mossotti equation, when we make the calculation for epsilon r, we will get 1.63. So the approximation that we use, namely that the dipoles experience simply the applied field, gives us a lower value for the dielectric constant than what Clausius-Mossotti gives us, namely that now we are taking the individual dipoles experiencing a particular local field that varies from dipole to dipole. Okay? So we are underestimating when we make that approximation. And the same kind of approach could be used for other materials to show to calculate the dielectric constant. Now, so far what we did, we just looked at atoms and we said they are going to be polarized electronically under the applied field because the electron cloud moves one way and the positive charge the other way. We have an interesting situation when we talk of covalent bonds, covalently bonded solids. As we know, in covalently bonded solids, there are valence electrons that are localized between atoms. Okay? They form the bond. Now, that doesn't mean that they are rigid because they can tunnel. They are localized in the sense of they spend more time there, but there is no particular electron that is stuck forever in one place. We don't mean that that particular electron is always there. It's a delocalized function. There are other electrons that move in there, it goes. But on an average, we have a higher probability of finding electrons between the atoms. That's what we mean by the covalently bonded solids. Now, what happens to these kind of valence electrons under the presence of an applied field? The core is very rigid, and it's very solidly bonded, these ionic cores. And then we have these electrons that are in between there. And under the influence of this, we see that unlike where we just simply considered the average electron cloud around an unbonded atom, which could also produce electronic polarization, these valence electrons that are there are actually much more significantly shifted with respect to the earlier case where simply we're looking at the average unbonded atom. And so in covalently bonded solids, the shift that we have in the valence electrons is much more significant than in the case of the unbonded atom. Even in the unbonded atom, we saw we can have electronic polarization. But here, the particular example of electronic polarization, the electrons experience a much greater shift. We've got a very rigidly bonded core of nucleus, the positive charges, and the valence electrons are also localized, and they experience a very significant shift under the applied field. And as a result of this, we see that in covalently bonded solids we can have a very high dielectric constant because we are creating strong dipoles. You can think of it this way: the energy that is required to break the covalent bond, for example in silicon, is about 1 to 2 eV, in that range. On the other hand, if you had an ionic silicon and you wanted to remove the electron from there, the energy required to remove one electron is about 10 eV or so. So when you want to move things around, in the case of the covalent bond, that shift will be more than in the case of the ionic solids. As a result of which we can have, for example, in silicon, a relative permittivity of something 11.9, pretty high. And they say for germanium, it is around 16. So it's same electronic polarization we are talking about, except we are dealing specifically in this case with the shift in the valence bonded electrons. Okay, I mentioned at the beginning that there are different mechanisms of polarization, and one of which we have seen so far is electronic polarization. What I'd like to do is to take up the remaining methods of polarization or mechanisms of polarization. Oops. We already saw one, and the rest that we will look at are ionic, orientational, or dipolar, sometimes it is referred to as, and interfacial. Okay, these are the different mechanisms of polarization that we will consider in turn. Let's begin with ionic polarization. For example, we have NaCl. Obviously, from the name ionic polarization, it means that it's related to ionic solids. We got potassium chloride, lithium bromide, these kind of solids where this will be significant. Now, in this case, we have got ion pairs, positive and negative ions that are there. And in the solid, because it's a crystal structure, they're located at specific lattice sites. And usually they're sort of alternating. You've got a positive charged sublattice, and you've got a negatively charged sublattice, and overall neutrality is maintained. Now, if we consider these, they have no net dipole moment in the solid, because the way they are arranged is something, just looking at a one-dimensional picture, that I'll say have negative, positive, negative, positive, and so on. Okay, just looking at a one-dimensional picture, they are arranged head-to-head like this. Now, in this case, between this and this, it forms a dipole. And which way is the dipole moment aligned? How did we define it? From negative to positive. So I've got a dipole moment that is this way. But between these two ions also I've got a dipole moment the opposite way. And when we look at the overall dipole moment, they are same in magnitude because they are dealing with the same kinds of ions. I've got no net dipole moment. Now, what happens when I apply an electric field? So in this case, there's no field. Okay? And when I apply an electric field, the negative ones are going to move in one direction, all of them, and the positive ones in the other direction. And therefore, there will be a shift. Okay? So you can imagine all these are moving in this direction, and these are moving in this direction. So alternatively, there will be a compression kind of coming together of the negative and positive. These will come closer, and there will be a spacing difference. So we will get something like this, the negative ones moving in this direction and the positive this way if we have applied field, namely something like this, because they've moved, shifted. As a result of which now, this is my one dipole moment, spacing is this much, and the other one, the dipole moment is this. So instead of now being alternately equal and opposite, I'm ending up with a net dipole moment in the presence of an electric field. This is a schematic one-dimensional representation of the picture. Okay, because of the shift in these, I'm creating this dipole moment under an applied field. So we can write a P average dipole moment per ion pair. Now we're talking of pairs of ions, so average dipole moment. Remember, in the case of electronic polarization, the shift is all within each atom, and so number of atoms or number of molecules would give us the correct answer. Here we are talking per ion pair. It's simply now some other value. I don't remember if I put the notation dash and, to indicate that it's a different value from the previous case, and we have a net value. And all we'll say at this point is that it's proportional to the applied field. You increase the applied field, we will get a larger net dipole moment. Now here also we can write it as the P average is equal to some polarizability times field. So the constant there is my polarizability, except that I'm using the symbol I to indicate ionic polarizability instead of E, which we used for electronic polarizability. So similar kind of expression as before. It turns out that the ionic polarizability is often 10 or more times greater than the electronic polarizability. It's much more stronger, the effect, than electronic polarizability. As a result of which, the dielectric constants or relative permittivity in ionic solids is also very high. When we consider it in terms of polarization, we can write then that P as before, the polarization is equal to N, where we are not talking of the molecules now, the number of ion pairs. Okay? Per unit volume. Times the average dipole moment, which we now express as Ni alpha I. If you want to account again for the correctness to use the local field, then either it's the, if you take the approximation, we will use the applied field, or to be more exact, we use the local field. And using again the same kind of approach as before, going through the equations, you will end up also here also with the similar expression relating the relative permittivity to the polarizability. Except that now we have Ni alpha I. So it's the same Clausius-Mossotti equation, except that you have now this term instead of N alpha E. Okay. So as far as the electronic and ionic polarizabilities are concerned, we are able to use a similar approach and arrive at this expression. Now in addition to this, we also must remember that even in ionic polarizability, where the material can be polarized ionically, electronic polarizability is also present. So both these are happening there, though not ionic polarizability is not there in all the materials. That's the difference. So here we have both effects. Now if we come to the third kind, which is known as orientational polarization, it's also referred to as dipolar polarization. We're talking of molecules that have a permanent dipole. Which we will call P naught. So the dipole moment exists whether or not there's a field. It's a permanent dipole. An example of that might be HCl, hydrogen chloride. That's chlorine and that's hydrogen. And the dipole moment is. So you can imagine, say, where you've got large differences in electronegativity, then we can create things like this. Even in liquids or gas phase, this is common. By common, again, it's a relative term. But in solids, it's difficult. We will see an example, glass, some kinds of glasses, for example, where this is the case. And we'll understand why it is not so easy in the case of solids. So we'll stick for now to the, for sake of argument, with the liquids or gas phases. It can be extended to the idea of solids too. As long as we've got field is equal to 0, in liquids or gases, even though there's a net dipole moment, due to thermal agitation, dipoles are randomized. Right? What do I mean by that? Though there is, each of them has got a net dipole moment, they all sort of point in different directions. And so on an average, we don't observe any dipole moment in these materials. That picture changes when we apply an electric field. And what the field will try to do, just as you have for magnetism and things like that, will try to align these dipoles along the field. So what will happen then is that the hydrogen ion will want to move in one direction, and the chlorine moving in another direction in response to this field. It will try to align it. So if the field was one way, we'll look at it a little more closely next, and the dipole moment was like this, some particular one, it's going to try to move these so that it gets aligned properly. Okay. So in the specific case that we will consider, I won't go into the full derivation of it. We've got this aligned at some angle theta along, with respect to the field. So the dipole moment built in is P naught between the negative and the positive ion, and the net dipole, the particular dipole moment is sitting at some angle theta to the field. And so what the field is going to try to do is to move this in this direction, okay, where that's the force is acting in this direction is simply charge whatever is there on it times the field, and this one will be moved in this direction where you got the opposite force. The net result of it is, because these are bonded together, they can't simply move wherever they want to go off to, and so a torque is set up around the center of mass. We give the symbol tau, which is for torque around the center of mass. So instead of them just freely moving off and aligning themselves with the field, because they are bonded together as part of the hydrogen chloride molecule, or whatever we are considering, the particular example was HCl, it will seek to rotate it, and there will be a torque tau experienced by this molecule. We are neglecting something here, that the effect of this field will also be to slightly stretch the bond. Okay, this and this will slightly get stretched, but that's a smaller effect compared with the alignment trying to orient it, the torque that is there trying to orient it around the center of mass. If all the dipoles rotate and get aligned, then my polarization is simply there's n dipoles times the permanent dipole moment. I had n dipoles per unit volume in there, and they've all been aligned along the field now, and we end up getting n times P naught, which is the permanent dipole. But due to thermal agitation, not all will get aligned. So there's two competing effects here. One, the field that is seeking to align it, and one that is thermal agitation that is seeking to destroy the alignment and make it randomized. So we end up with some average value. So polarization is equal to n times P average. Not the whole, all of them are aligned, because some are going to remain misaligned, and so there's going to simply have some average value, which will be less than this case. So if all were aligned, it would be this. Since only some are going to be aligned and not all because of this thermal agitation, we get some average value times n. This polarization that is occurring in this fashion is what is known as orientational polarization. Now we would like to know what is P average if possible. And to know this, we have to determine what is the energy of the dipole, potential energy, in the field E. Okay? That's one effect, is trying to align it, so we'll know some energy consideration there. And then there's also thermal energy seeking to randomize it. So these are the two competing effects that we must know in order to determine this. Now if the relative magnitudes of this will determine whether at any given temperature we see the orientational polarization or not. If the temperature is high enough, then thermal energy will be the one that dominates, and the dipole will not be aligned, and so we end up having no effect of the field on it. We won't see dipole polarization. Now for examining all this in detail, we would have to apply Boltzmann statistics. That will allow us, how is the energy distributed, potential energy distributed for this collection of molecules or dipoles and so on. And we use all that as long as this condition holds good, namely that the average dipole moment times the field is less than kT. This is a condition that normally is under normal conditions of temperature and all hold good. The average dipole moment due to orientational polarization can be expressed as 1/3 P naught squared field by kT. Okay. Strictly speaking, again, if you want to be more accurate, you would use the local field idea, what the exact dipole is experiencing and not the simple average value. What we see here is that we've got a temperature dependence to this whole thing, which we did not have for the electronic polarization or for the ionic polarization. There is a T term here. And so orientational polarization is strongly temperature dependent, whereas the others were temperature independent. We can use this, and by comparison with the previous cases, we can then write P average is equal to alpha D times E, whereby comparing with the previous equation we have that alpha D, which is the dipolar polarization, dipolar polarizability per molecule, maybe strictly dipolar orientational polarizability because it is related to orientation, is simply by comparison with the previous equation 1/3 P naught squared by kT times the E here. That's what we had written earlier. So since this temperature dependence is there in alpha D, as temperature increases, we find that alpha will what? Decrease. And correspondingly, because alpha is related to the permittivity or dielectric constant will also decrease. That is the dielectric constant that is related to orientational polarization. The others are not related to temperature, ionic and electronic polarization. Predominantly, this type of polarization can be seen, I said, in gases and liquids. Let me give a few examples. Polar liquids, water, alcohol, acetone, and so on. We'll also see it in polar gases. The example we just looked at was one, namely HCl. Another example would be steam. We see it in some solids. Again, there must be a permanent dipole built in. But the problem with the solid would be what? Why is it difficult to see this kind of polarization in solids? Therefore, crystal structure is there, so what? Very good. I mean, because of the rigidity, that's the idea you were expressing. I was just trying to draw that out a little further. That, remember, here it is something that is going to rotate. And in a solid, it is going to be very difficult for the parts of it to rotate because they are all rigidly held together within a structure. Nevertheless, it is seen in certain types of glasses where the structure is more open. It's amorphous kind of structure. And it's strictly not simply a rotation. It may involve actually an ion jumping from one side to the other side. Under the influence of this torque, it may involve the ion is jumping because again it's part of a rigidly bonded solid, and so you cannot simply rotate it easily. But because of the nature of the network that is there in amorphous solids, the sites are not so specific, they are not so fixed. It's random, more or less, and therefore we can see it in these kind of glasses also. We come to the last mechanism of polarization, namely interfacial polarization. Here the basic idea is that the charges accumulate at some interface. For various reasons, they will build up at a certain interface, they can't move further, and then when they are building up there, they add to the dipole moment. Okay, some interface where they can't cross, they get stuck there, and as a result of which they build up higher polarization. Take an example of that. The most obvious one we looked at is that we have got some kind of dielectric sandwiched between two metal electrodes, and the field is applied here. We know that in the electrodes, the charge transport is by means of what? It's connected to some voltage source, obviously. So in the electrodes, the charge that is there, what kind of charge is it? In a metal electrode? Electrons, right? That is connected to a voltage source, and that will replenish the electrons, and as the polarization changes, the amount of charge that is stored will change and so on, but it's all coming out of electrons and holes, if you will. Some positive, some negative, surplus or excess, surplus or lack of electrons. But what is happening inside here is that charge transport is primarily taking place, say, in an ionic material due to ions that are moving. What happens when the ions come to this interface between the dielectric and the electrode? The ion simply can't go on into the metal, right? It will come to that interface and get stuck. It has nowhere to go. Even if it's being pushed by the field that is applied, it has nowhere to go. So if you look at it, that in some kind of the dielectric electrode where we have species, say the negative species are more fixed, we can have structures like that, and the positive charges are more mobile as a result of their size, for example. I'll give you a specific example, 5 of them. So initially they're all balanced, you applied the field, and when you did that, these positive charges will migrate to this electrode because they can move through the network. They're small, very small, but the negative ones are more or less fixed. Okay. And then what will happen is, the next view, if you look at it, is that the positive charges have more or less accumulated out here. And the negative charges may have shifted a little bit, but are more or less in their original positions. Now, we have applied a voltage here, so we've got charges that have, what we call the free charges yesterday, and in the two electrodes here. Now, as this charge keeps on building up here, to compensate for that, we will get more electrons flowing into this electrode. So there's going to be charge build up there at this. Now, these ions simply can't cross over into the electrode, and as a result of which now, we've got initially the separation, the dipole moments that would have been here are very different. Now I've got them all piled up here, and with respect to the negative ions here, we've got a whole different set of dipole moments. They've all been moved far away from there, on an average, moved far from their nearest neighbor, whatever negative charge was there. They've drifted. And it is this additional dipole moments that are created is what is contributing to interfacial polarization. That's one mechanism. I just mentioned this kind of, I didn't give you an example. For example, lithium is one example, being a very small positive charge, or hydrogen that can migrate through a dielectric like this. These are some specific examples. They are put to good use actually in practical situations, but their very size means that they are able to migrate, whereas the bulk of it, the negative charge, remains fixed in its place. Another example of how interfacial polarization might work is, let's say again you've got a material between two electrodes, except that there is, say, another grain. There's two grains are there. Okay, so this is a grain boundary, or some other kind of phase, two-phase material. Again, the same problem comes, that when it gets to this boundary, it's stuck. So even within the material, without even going out to the electrodes, we may end up with charge buildup. The ions have migrated within this in one direction and the other, the charges, but when they got to the interface, they got stuck, and now they start attracting the oppositely charged charges there around it. Excuse me. So even in such a situation where we have, say, a second phase or a grain boundary, the same kind of interfacial polarization effect may be seen. A more common situation these days may be where we have composites, where you have a matrix and inside it a dispersed phase, small particles of a dispersed phase. Now, at each of those boundaries where we have the dispersed phase in contact with the matrix, the same phenomenon will occur. So if there's dielectric behavior there, then that adds up to the interfacial polarization. Now, unfortunately, interfacial polarization is something that is structure dependent, processing dependent, depends on the particular nature of these boundaries that have formed or how they have been dispersed and so on. So it's not as easy to treat it and give it some average value like we did for P average for the electronic or ionic cases and so on. So we simply cannot club it in with the rest of it and treat it in the same way. So there is no simple equation that will allow us to say, okay, the average value of the dipole moments that are created. It will depend on where the grain boundary is and how many grain boundaries are and so on. So that's the difference. But this is a real kind of polarization that depends on the particular structure. So now I've got these four different mechanisms: electronic, ionic, orientational, and interfacial polarization. What do I do with them if I want? I've got a whole material. I've looked at their individual things. Can we simply add it up to look at the total dipole moments or the total value of the polarization? The answer is that as long as we are dealing with only, as I said, the ionic and electronic polarization is fine. So as long as we are dealing with the ionic polarization, electronic polarization, we don't have much of a problem. And to some extent we can include even the orientational or dipolar effect. But we have to leave out the interfacial. We can't just add that on, because this is an average value per molecule. Remember that, the dipole moment per molecule. Now, depends on the particular nature of the grain boundary and also I can't simply add it on here. But for these, we can more or less deal with it. Now, in this form, I said we simply cannot get a simple relationship with the Clausius-Mossotti equation to know the relationship between P average and the between epsilon r and alpha. So, as long as we are dealing with only these two, we can come up with a simple relationship, namely that P average, which is equal to alpha E for the electron polarizability times the local field plus alpha I times the local field. We treat only these two. And I have expressions for these in terms of the Clausius-Mossotti equations. So I can combine this now and write it as epsilon r minus 1 by epsilon r plus 2 is equal to 1/3 epsilon naught n E alpha E plus Ni alpha I, where we've looked at each of these terms before. Ne is electronic, the number of atoms there we had seen, or molecules per unit volume. Alpha electronic polarizability. Here is the number of ion pairs per unit volume, and so on. So, as long as we treat simply ionic and electronic polarizability, this is fine. I don't know if I have time to go. It seems like I should have a few minutes. So, frequency dependence, I will start off, and I'll see if I can complete it in the next lecture. If I don't, I mentioned right at the beginning that these properties, the dielectric constants, have a frequency dependence. And I also mentioned that similar to resistors, there are losses involved in storing charge in dielectric materials. These losses also have a frequency dependence. I just mentioned that at the beginning of the class, and I said we'd look at it. Now you can imagine that what would happen if we consider each of these four mechanisms in terms of their frequency dependence. Somewhere where charges have to be transported across larger distances and so on, under static conditions DC it's okay, but now I apply AC. And as I increase the frequency, what's going to happen, once the electrode, this is positive, this is negative, now I'm flipping back and forth and I'm increasing the frequency. One by one, various mechanisms will drop out which cannot respond to the frequency. And what we will see is that the interfacial polarization is the one that will function at the lowest frequency. I mean, all of them will be there at low frequencies, but the first one to sort of drop out of the picture because it cannot respond to the higher frequency is interfacial polarization. And then the next one to go will be orientational. It was moving this way, now it has got to go and back align it. And then we will see that ionic polarization, where now ions are moving over short distances, is the next one that will be there, along with electronic polarization. And electronic polarization is the one that lasts up to the highest frequencies because it simply involves within the atom small changes. So that's the one that can respond to the highest possible frequencies compared with the other mechanisms. So that's the basic understanding about the dependence of frequency for these mechanisms. And similarly, we see that the losses that are associated with them also have a frequency dependence. There's a maximum at certain frequencies, and other frequencies the losses are negligible. So we will look at that in the next class. I think my time is up, though the watch is a little different there, but I think my time is up for this lecture. So we will look at the frequency dependence both for the relative permittivity or dielectric constant as well as for the different losses that are there. Okay, so we'll take that up in the next lecture. I hope to finish dielectric materials in the next class, and then we'll have 2 lectures on polymeric materials or organic materials that are used in electronics. So that should wrap up our course. I'm giving you just a brief glimpse at some of these things. All right.